We are billions of kilometers away from Earth in intergalactic space. Between the Milky Way, our own galaxy, and Andromeda, another galaxy with hundreds of billions of stars, we are adrift in space. All around us, there is almost no matter. We have no place in all this chaos. A web weaves itself all around us. Spacetime is the web that encircles the entire cosmos. With the help of this hypothetical grid composed of a vast number of tiny particles, we will be able to see the unseen, comprehend the universe's architecture, and grasp its dynamics. Hello, and welcome back to Z. Today, let's take a visual tour through time and space together. The grid appears serene and unmoving from our current location. It is unaffected by anything, and if we toss a marble at it, it shoots forth straight and disappears into nothingness. The grid is not perfectly static in reality. Fast-forwarding reveals that it drifts ever so slightly, much like a river whose current carries everything with it as it flows into the stars. Stars, gas clouds, and dark matter significantly distort space-time, drawing the universe's fabric towards them. The Milky Way and Andromeda will eventually combine to become one in several billion years, long after we vanish. This is happening very slowly. Even though Andromeda is moving closer, most galaxies are actually moving away, as scientists discovered at the start of the 20th century. The universe as a whole is constantly expanding. The grid swells more and more, separating galaxies like a stretched piece of fabric. As a result, their light is expanding and becoming redder in wavelength. As of right now, we understand that the enigmatic dark energy is what is causing this growth to quicken. The expansion began 13.8 billion years ago. The cosmos, a mush of varying energy, would have experienced extreme pressure and reached astronomical dimensions in an instant. The Big Bang occurred at this time. What existed prior to that? Really, nobody knows. The tiny oscillations, which eventually became enormous and condensed into filaments, halos, galaxies, and stars, would have drawn matter. We currently reside close to the Sun, one of these stars. Numerous bodies orbit the Sun, including planets, asteroids, and comets that travel freely through the universe's grid. The Sun's enormous mass curves space-time, causing everything to gravitate towards the star. The planets circle the Sun in this manner. They do not veer off course. They advance in a straight line, but the river keeps drawing them back toward the center. Planets likewise draw the universe's grid toward them, though to a lesser degree. For instance, the Earth holds the Moon, its natural satellite, and all our man-made satellites. The Earth bends space-time, preventing the International Space Station from traveling too far despite its high speed across space. At a distance, the grid moves slowly, so an object moving quickly enough may easily avoid the pull. However, as we approach the center, the flow gets denser, and the grid accelerates more. Rockets on Earth's surface have to accelerate to extremely high speeds in order to lift off the ground and leave the planet. The apples will come together in one direction and stretch apart in the other if we drop multiples of them next to each other. The grid converges towards the center. We refer to these as tidal forces. The Moon acts in a similar manner on Earth, forcing the water on its surface to move. The Earth's rotation is what drives the tide's oscillations back and forth. It takes about a day for it to rotate. The motion of all its mass impacts space-time, causing a slight pull on the grid as it rotates. The revolution of our planet affects the apple from a distance, slightly distorting its orientation and course, even if it doesn't come into contact with Earth during its drop. The grid is still descending into the Earth. The minerals that make up our planet resist its attempts to pull everything toward the center. They push very hard outward to keep from collapsing in on themselves. After a jump, we experience this pressure in our legs as we descend to the ground. The river converges at the center, where a marble, if it could survive the tremendous pressure of the Earth's core, would remain immobile. All of the grid's constituent particles go forward and bounce back after reaching the center, only to resurface outside of the Earth. If we could leap through the entire world, we'd emerge on the other side. Eventually, our star will perish in 5 billion years. The sun won't be able to continue producing pressure and obstructing the grid's flow. Its atmosphere will gradually grow into a massive planetary nebula, while its core will collapse in on itself to produce an incredibly dense white dwarf. Not all stars fade away in this manner. Another star, a supergiant, is also depleting its fuel a few hundred light years away. Its internal pressure can no longer support its entire mass, despite it being 20 times more massive than the sun. When the core bursts, the outer layers resurface and explode into a supernova. Further compression of the core forms a neutron star. In a region about 30 kilometers wide, it holds the mass of 2 suns. The universe's grid tugs so strongly that it drags light along with it, resulting in strange optical distortions. An even more massive star, located a few thousand light years away, is on the verge of exploding. The star swiftly blasts away its outer layers, propelling its core toward the center. The universe is more powerful this time. Unable to resist, it pulls the star's core toward the center, where all of the mass condenses into a tiny sphere. Because of its bent nature, the fabric of the universe falls faster than light. Nothing can break free from this terrible cycle. Everything moves in a downhill direction. It is not possible to remain motionless or even communicate with others. This is what we call a black hole. Some black holes in the cosmos originate next to other stars and absorb their substance, which takes the form of plasma at extremely high temperatures. As the plasma enters the black hole's orbit, it creates an accretion disk that spirals toward the horizon while losing energy. Near the black hole's center, the flow accelerates to an infinite speed and causes severe object disintegration. The grid expands with such ferocity that it spaghettifies every body and splits atoms apart. Our existing theories fundamentally fail to sufficiently describe the quantum behavior of spacetime. Nothing in the cosmos is constant. Almost all stars revolve around themselves. When a star dies, it rotates faster than an ice skater tucking her arms next to her body, and its core compresses to form a black hole. This rotation weaves spacetime itself together, and it continues to rotate thereafter. The black hole's ergosphere transports the entire grid into a vortex that rotates bodies in the same direction as light below a certain point. The black hole forces everything to rotate, including light. A black hole of this kind would possess a second internal horizon beneath the event horizon, where spacetime's spin produces a centrifugal force that counteracts gravity and slows down the grid's descent. In mathematics, white holes extend these internal boundaries, allowing us to explore alternate universes. But a black hole's inner horizon is incredibly unstable and, most likely, non-existent. Most of the structure at the center of a true black hole is still unknown. In the end, 2 black holes can dance together, drawing each other faster and faster until they combine to create a single, larger black hole. This new black hole vibrates until it stabilizes, resembling a bubble. During such an event, the vibration drives the entire fabric of the universe. Gravitational waves, greater in strength than all the stars in the sky, form and vanish at the speed of light, warping everything in their path. After traveling for more than 1 billion years, one of these vibrations finally reached Earth on September 14, 2015. The Earth shook by a tiny amount. However, researchers using detectors could now measure these vibrations for the first time in history. They observed an enormous merging event that took place over 1 billion years ago. This led to the advent of gravitational wave astronomy in 2015, which has allowed us to study the universe's structure itself. In conclusion, our journey through the cosmos, from the serene grid of space-time to the violent dance of black holes, reveals a universe in constant motion and transformation. The interplay of gravity, energy, and matter shapes everything we see and don't see, from the smallest particles to the largest galaxies. Understanding these cosmic dynamics not only helps us grasp the fundamental nature of our universe, but also deepens our appreciation for the delicate balance that allows life to exist on our tiny planet. As we continue to explore and learn, Each discovery brings us one step closer to unraveling the mysteries of the cosmos. Thank you for watching and see you next time.